Hello, welcome to another module in this massive open online course. So, we are looking at the Fourier analysis for discrete time aperiodic signals through the DTFT, discrete time Fourier transform, alright, and we are looking at the properties of the DTFT. So, let us continue our discussion on that. So, we are looking at the discrete time Fourier transform . And the next property, so you looked at several properties, we have looked at the duality. The next property that we want to look at is differentiation in frequency. Of course, in time it is a discrete signal, so we cannot talk about differentiation in time. So, this is differentiation in frequency. What happens when you differentiate in frequency? So, we have x of n, let us say, as the DTFT capital X of omega, alright, which means basically your x of omega equals summation n equals minus infinity to infinity x n e raised to minus j omega n. Then if you differentiate this, dx omega over d omega, that is n equals minus infinity to infinity. If you take the differentiation sign inside, x n is a constant, that is d of derivative d over d omega of e raised to minus j omega n with respect to omega. So, or let me just write it, that is d over d omega e raised to minus j omega n, which is summation n equals minus infinity to infinity x n minus j n e raised to minus j omega n, which is minus j summation. So, dx omega over d omega, that is n equals minus infinity to infinity minus j summation n equals minus infinity to infinity n x n e raised to minus j omega n. So, this is basically, if you look at it, this is basically the DTFT of n x n, okay, of the signal n x n, okay. And therefore, this implies if you bring the j to the other side, this means j dx omega or d omega equals summation n equals minus infinity to infinity n x n e raised to minus j omega n, okay. And therefore, we can conclude that n x n is basically has the DTFT, which is j dx omega over d omega, all right. So, next property is the differencing property. Since we cannot differentiate in time, one can difference the differencing in time, which means if x of n has the DTFT x of omega, what can we say about the difference signal x n minus x n minus 1? What can we say about this? This is the difference signal or the differential signal, all right, x n, the successive differences, sometimes also called as a differential signal, all right. So, that is your basically your delta x in time. And now if you look at this, if you take the Fourier transform of this, you can see it is very simple, this is x of omega minus the Fourier transform of x n minus 1, that is e raised to, that is the delay in time leads to modulation in frequency, e raised to minus j omega x omega equals x tilde omega, which implies x tilde omega, that is the DTFT of x n minus 1 equals 1 minus e raised to minus j omega into x of omega. So, basically x n minus, so if you look at this, you have x n minus x n minus 1 has the discrete time Fourier transform 1 minus e raised to minus j omega into x of omega. Okay. So, this is basically the discrete time Fourier transform. Let us now look at another property. So, all these are small properties, but fairly useful in the manipulation and analysis of DTFT of signals. A lot of these properties can be used together to derive the final DTFT or to analyze the system or signal under consideration. So, let us consider the accumulation n equals or k equals minus infinity to n. That is, you are accumulating all the samples of the signal x k until sample n. You can see this is very similar to the integrator, which basically integrates the input signal x t. All right. In analog time, the analog, all right, the corresponding system in analog for an analog signal or for a continuous time signal is the integrator. Okay. So, basically it integrates or accumulates the signal at a certain time. In the discrete time, we are basically accumulating all the signal samples. So, basically if you look at the continuous time analog, that is minus infinity to t x t dt. So, this is similar to the integrator. Similar to the integrator for continuous time signals, all right. And now, the Fourier transform of this is given as pi x of 0, you can show that pi x of 0 into delta omega plus x of omega over 1 minus e power minus j omega. So, that is basically your accumulation, that is your integral n equals, that is your summation k equals minus infinity to n x k, that has the DTFT that is given as pi x 0 delta omega plus x of omega divided by 1 over 1 x of omega divided by 1 minus e raised to minus j omega. All right. So, that is basically the result, for accumulation of a discrete time signal. Okay. Let us now proceed to another important property, that is the convolution, because we have seen this several times before. Convolution is always a very important relation, a very important property in the analysis of signals and systems, because the convolution describes the output of a linear time invariant system to any input, either continuous time or discrete time. Okay. So, the next property that we want to look at is basically the convolution, and now the convolution of two discrete time aperiodic signals. And convolution is always very important, as I have said, because it is very closely related to the properties of LTI systems. Okay. So, y n, which is the convolution of x 1 n into x 2 n, which means this is equal to the summation m equals minus infinity to infinity x 1 m x 2 n minus m. And now we want to find what is the DTFT of yn, given of course the DTFTs of x1n has a DTFT that is x1 omega and x2n has the DTFT that is x2 omega. And now you can see this DTFT y of omega can be obtained as follows. So, y of omega equals summation, that is y of n equals minus infinity to infinity, y of n e raised to minus j omega n, which is basically I can always write this as summation n equals minus infinity to infinity, substitute the expression for y of n, that is m equals minus infinity to infinity x1 m x2 n minus m into e raised to minus j omega n. And now I can always write this as summation n equals minus infinity to infinity summation. Now I can interchange the summation with respect to n and m. So, interchanging the summation, I am going to describe this by this arrow. So, first you have the summation m equals minus infinity to infinity, then x1 m will come out because it depends only on m, n equals minus infinity to infinity x2 n minus m e raised to minus j omega n. This is DTFT of x2 n minus m, that is x2 n delayed by m samples, x2 n delayed by m samples, hence the corresponding DTFT is naturally x2 omega e raised to minus j omega m, that is modulation in frequency. Okay. So, that basically gives me summation m equals minus infinity to infinity of x1 m e raised to minus j omega m into x2 omega, and now if you look at x1 m into e raised to, so I can write this as x2 omega m equals minus infinity to infinity x1 m e raised to minus j omega n, which is nothing but basically x1 omega, and therefore, what we get is y of omega, which is the convolution y n, which is the convolution of x n, x1 n, x2 n, has the Fourier DTFT, that is x1 omega into x of omega. So, the net result is that x1 n convolved with x2 n has the DTFT x1 omega into x2 omega. So, convolution in time implies multiplication in frequency, similar to what we have seen several times before. Convolution of two discrete time aperiodic signals leads to a multiplication of their discrete time Fourier transform. So, basically I can summarize this as convolution in time multiplication in the frequency domain. Okay. So, when you convolve two signals in time, the corresponding DTFTs, correct, in this case are basically convolved in the frequency domain. Okay. All right, let us look at similarly for multiplication in time. Again, the dual of that is basically it has convolution in the, similarly let us consider multiplication in time, that is, if you look at two signals x1n into x2n. Now remember, the x1 omegas are periodic, hence this is the periodic convolution, okay, 1 over 2 pi x1 omega periodically convolved with, because remember the net DTFT also has to be periodic, correct, when you convolve to a periodic signal. Remember the DTFT is always a periodic signal, so you cannot perform a general convolution, but you have to convolve in such a way that the resulting output is periodic, and that is given by the periodic convolution, okay. So this is basically the periodic convolution of x1, the periodic convolution of x1 omega with x2 omega, which is basically 1 over 2 pi over 2 pi x1 theta x2 omega minus theta d theta, I am sorry, this is d theta, okay, and this is for any contiguous, this is for any period 2 pi, this is a periodic convolution, this is over any period 2 pi, okay. Now some other properties, if xn is real, let us consider a real signal, then I can always express a real signal as the sum of even and odd components, okay. So this is the even component xcn, the even component xon, this is the odd component. We have we have seen that you can always do this, that is xcn, the even component of a signal is xn plus x of minus n by 2, the odd component is xn minus x of minus n by 2, we can always do this for any real signal, okay. And now further, if I can express the DTFT of xn as a omega plus, so in general the DTFT of xn is complex. If you can express it as a omega plus j times b omega, then it can be shown that, and this is something that can be shown, that is xn has the DTFT that corresponds to the real part of the DTFT of xn, that is the even component has the DTFT a omega, that is real part of the DTFT x of omega, and similarly as you can expect, the odd component has the DTFT that is given by j times b omega, okay. So the even component has a DTFT that is a times omega, that is the real part, and the odd component has a, so the DTFT of the real part, even part of the purely real signal, you can see is basically real, and the DTFT of the odd part, odd component of this real signal is purely imaginary. You can see that j times b of omega, this is purely imaginary, okay. This is purely imaginary. And now further, since we have a real signal, recall that for a real signal x of conjugate of minus omega equals x of omega for a real signal xn, where x omega is the DTFT of, this is true for any Remember, this is true for any real signal xn. So, this implies that if I take the DTFT a of omega plus j b of omega, this is x of omega, this must be equal to x of minus omega conjugate. So, a minus omega j b minus omega conjugate. Okay. So, this must be equal to a of minus omega plus j b minus omega conjugate, and this implies that a of omega plus j b minus omega equals, well, a of minus omega minus j b of minus omega. Now, equating the real and imaginary parts, equating real comma imaginary parts, we have a of omega equals a of minus omega, okay, which implies a of omega is a even function, and further we also have b of omega equals, you can see equating the imaginary parts, we have b of omega equals minus, I am sorry, this has to be b of minus omega. So, this is basically b of minus omega. Okay. So, b of omega equals minus b of minus omega, which means this is an odd function. So, a of omega for a real signal, the real part is an even function of omega, real part of the DTFT, and the imaginary part b of omega is an odd function of omega. Okay. Now, therefore, if xn is real and even, now what does this imply? This implies two things. One, xn equals real plus even, this implies xn equals xc of n, comma xo of n, the odd component of n is 0. So, this implies x of omega equals a of omega, which is basically real and even. So, for a real and even signal, the corresponding DTFT is, so if the signal is real plus even, okay, the corresponding DTFT is real plus also even. On the other hand, if the signal is real and odd, okay, now look at the other thing. If xn now this implies that xn equals the odd component, okay, the even component is 0. If xn is an odd signal and xc of n equals 0, and this implies x of omega equals x odd component of omega, which is equal to j b of omega, which is purely imaginary and odd. Remember, b of omega is odd and this is a purely imaginary function. So, this is purely imaginary plus odd. So, if the signal is real even signal, its DTFT is purely real and even. If xn is a real and odd signal, then its DTFT is purely imaginary and odd. Okay, so this is the important thing to keep in mind. Okay, all right. So that basically sums up the properties of the DTFT of real signals, real and even, real and odd signals. Okay, all right. And then what we can also do, so as to sort of to complete this, we can look at the Parseval's relation, that is the last topic, one of the last properties that we can look at for the DTFT, that is the Parseval's relation. And this is also very simple. Remember, previously we have said, let us say we have yn equals x1n, that is the multiplication of x1n and x2n, then we know that y of omega is the periodic convolution of x1 omega and x2 omega. So, that is given as integral 1 over 2 pi integral over any 2 pi region x1 of theta x2 of omega minus theta d theta, which implies basically that now if I look at summation, so now we have basically what do we have? We have basically summation n equals minus infinity to infinity yn e power minus j omega n, this is equal to y of omega. Now, if you set omega equal to 0, now in this set omega equal to 0, what this implies is summation n equals minus infinity to infinity yn equals y of 0, implies summation n equal to minus infinity to infinity the product x1n into minus infinity to infinity x1n into x2 of n equals y of 0, and y of 0 is nothing but set omega equal to 0 on the right. So, that is integral x1 of theta x2 of minus theta d theta, and you can also in fact write that as theta is just an index. So, in fact you can also write that as 1 over 2 pi integral over 2 pi x1 of omega x2 of minus omega d omega. Okay. This is summation x1 of n x2 of n. Okay. So, you can always write this thing, okay, summation n equal to minus 1. This is nothing but the correlation between these two discrete time sequences x1 and x2n, summation n equal to minus infinity to infinity x1 and x2n, that is integral 1 over 2 pi integral over any 2 pi x1 omega into x2 minus omega d omega. Okay, I have simply replaced the integration variable theta by omega. Okay. Now, if we set x2n now in this, so this you can think of this as the generalized Parseval's relation. In fact, this is a step ahead of the Parseval's relation, it is much more general. It talks about two different signals x1n and x2n. So, you can think of this as a generalized or a general form So, you can think of this as a general form of Parseval's relation. Now, if you set x2n equals x1 conjugate n, then what you have is x2 of omega equals x1 conjugate of minus omega, because conjugate sequence is x1 conjugate of minus omega, which means x2 of minus omega equals x1 conjugate of omega. So, if you substitute x2n equals x1 conjugate on n on the left hand side, what we have is summation x1n into x1 conjugate n, that is magnitude x1n whole square that is equal to summation 1 over 2 pi integral over 2 pi x1 omega into x2 of minus omega, which is x1 conjugate of omega, that is x1 omega into x1 conjugate omega of omega, which is magnitude x1 square into d omega. That is the sum of the energy over one period. In fact, this is not the energy, but you can think of this as the power, because you are dividing by 2 pi. So, this is the power of the, you can think of this as the power of the DTFT. Okay. So, this is the Parseval's relation for the this is the Parseval's theorem for DTFT. The summation n equal to minus infinity to infinity magnitude x1 n square equals 1 over 2 pi integral over any 2 pi region magnitude x1 of omega whole square d omega. Okay. All right. So, basically that completes our discussion of the properties of the DTFT. In the subsequent, in the next module, we will start looking at the DTFT and its properties with relation to LTI systems. All right. So, we will stop here and continue in the subsequent modules. Thank you very much.